Welcome to today's paper reading. Today's paper is titled, A Phase Transition Between Positional and Semantic Learning in a Solvable Model of Dot Product Attention. This paper was published on the AR14 preprint by Hugo and colleagues from the Statistical Physics of Computation Laboratory and Information Learning and Physics Laboratory at EPFL, Switzerland. In this study, the authors investigate how a dot product attention layer learns both positional and semantic attention matrices. They demonstrate that a simple architecture can learn to implement a solution using either mechanism. On the theoretical front, they analyze the learning of a nonlinear self-attention layer with trainable matrices in the context of high-dimensional data. They provide a closed-form characterization of the global minimum of the empirical loss landscape, showing it corresponds to either a positional or semantic mechanism. The study also highlights a phase transition from positional to semantic mechanisms with increasing sample complexity. Finally, they compare the dot product attention layer to a linear positional baseline, finding it outperforms the latter when using the semantic mechanism with sufficient data. In this introduction, the focus is on the significant advances made possible by the use of advanced technologies. These technologies, including AI, machine learning, big data analytics, and high-performance computing, have greatly impacted research outcomes. They enhance data accuracy, accelerate discovery rates, and improve problem-solving efficiency, thereby contributing significantly to scientific progress. The methodology focuses on self-attention layers, which are effective at extracting information from sentences by considering both the positions of words and their semantic meanings. The authors aim to expand the theoretical understanding of these layers. Key contributions include illustrating different solutions for the histogram task, describing a model with tied low-rank query and key matrices, and analyzing phase transitions and sample complexity. Experiments are conducted using Gaussian input data, and the performance of the dot product attention layer is contrasted with that of a linear attention layer. Figure 1 illustrates the existence of multiple solutions for the histogram task using a single layer of dot product attention. The sequence DBD is processed by embedding each token into learned vectors and adding absolute positional encodings. The attention matrix elements H are generated using key and query matrices Q and K, followed by softmax application. The schematic loss landscape in B shows two stable solutions. In C, the attention matrices for local minima are presented. The top row shows the attention matrix of the positional solution, which is largely independent of the specific input sequence. The bottom row shows the attention matrices from the semantic solution, which vary based on the input token. Both solutions achieve close to 100% test accuracy. Figure 2 illustrates the mixed positional/semantic teacher model with omega equals 0.3. The setting parameters are rs equals rt equals 1, l equals 2, a equals 0.6, 0.4, 0.4, 0.6, sigma 1 equals sigma 2 equals 0.25 id, p1 equals 1d equals minus p2, and q star operator tilde operator n, 0, id. The left panel shows the difference in training loss increment t between the semantic and positional solutions, with solid lines representing the theoretical difference from result 4.2 and markers indicating the experimental results from gradient descent. The middle panel compares the overlap theta, blue, between the learned weights q and the target weights q star operator, and the overlap m, red, between the learned weights q and the positional embedding p1. Solid lines represent the theoretical characterization from result 4.2, and markers represent experimental measures. The right panel presents the test mean squared error, MSE, with solid lines indicating the theoretical characterization from result 4.2 and markers showing the experimental MSC. The yellow line represents the MSE achieved by the dense linear baseline, as characterized by result 5.1. All experiments were conducted with d equals 1000 using PyTorch's full batch gradient descent for 5000 epochs with a learning rate of 0.15, averaging over 24 instances of the problem. Figure 3 illustrates the phase transition between semantic and positional training loss. The setup involves rs equals rt equals 1, l equals 2, a equals 0.6, 0.4, 0.4, 0.6, sigma 1 equals sigma 2 equals 0.25 ID, P1 equals 1D equals minus P2, and Q star operator tilde operator N, 0, ID. The color map shows the difference in training loss at convergence when training the model. 2. Using the PyTorch implementation of full batch gradient descent, initialized at P1 and Q star operator respectively. The green dashed lines indicate the theoretical prediction for the threshold alpha C, omega, above which the semantic solution of 7, in result 4.2 has lower loss than the positional solution. The experiments were conducted under the same conditions as in Figure 2. Figure 4 illustrates the phase transition between semantic and positional training loss. The color map represents the difference in test mean squared error, MSE, at convergence when training the model. 13. Using the PyTorch implementation of full batch gradient descent initialized at Q star operator, and the dense linear baseline. 15. The red dashed lines indicate the theoretical prediction for the threshold sample complexity alpha above which the dot product attention, 2, outperforms the baseline. 15. For comparison, the positional to semantic threshold alpha C, omega, is reminded in green. Experiments were performed as in Figure 2. In this experimental analysis, the authors explored the use of positional and semantic mechanisms within the attention layer. They characterized the global optimum of the empirical loss in a theoretically controlled setting, finding it corresponds to either a positional or semantic mechanism, with a phase transition observed as sample complexity increases. This asymptotic analysis of attention mechanisms' inner workings suggests several exciting research directions, including considering untied query and key matrices, appending a readout network, and addressing practical training procedures like masked language modeling. These extensions aim to enhance the theoretical comprehension of attention mechanisms. The related work section highlights several key areas of research. In neural network learning, the committee machine and transformers as statisticians are notable. The dynamics of message passing in dense graphs is also a significant area. For high-dimensional inference, the lasso risk for Gaussian matrices and high-dimensional asymptotics are crucial. Robust estimation via approximate message passing is another important topic. Regarding transformers and attention mechanisms, the study of inductive biases in self-attention, the impact of positional encoding, and the structure of vision transformers are all explored. These areas collectively provide a comprehensive background for understanding the advancements and challenges in the field. In this study, the model architecture is defined by the linear unit, LU, and the attention mechanism. The final prediction is derived using the argmax on the logits. The attention mechanism is formulated as a dot product, involving matrices Q, K, and V. The layer normalization is applied to standardize the input data. During training, all weights except those frozen to 0 were optimized using ADAM, achieving a test accuracy of over 99.8% on a dataset of 35,000 samples. The resulting parameter configurations, pose and sem, were found to be stable in the unconstrained parameter space. To verify this stability, the parameters were slightly perturbed and further trained using SGD for 100 epochs. Despite the training loss decreasing and test accuracy increasing, the qualitative behavior of the models remained unchanged, indicating that the configurations are in flat regions of the loss landscape. Table 1 presents the parameter configurations for different initializations in the histogram task, averaged over 10 runs with the same dataset. The table shows the accuracy and the L2 norm of the difference between the initial and optimized parameters for both ADAM and SGD optimizers. The results indicate that both optimizers achieve high accuracy, with ADAM slightly lower but more stable, and SGD slightly higher but with more variability. The L2 norm differences highlight the distance each optimizer travels from the initial parameters, with SGD showing a larger deviation. Thank you for watching.